Hello and welcome to the fifth part of the unit on magnetism. In this part, we're actually going to quantify the magnetic field due to a wire. If you have a current carrying wire, then the magnetic field equals mu naught I divided by 2 pi r. Mu naught is a constant, which equals 4 pi times 10 to the minus 7 Tesla meters per amp. I is the current and R is where are you relative to the wire. So if I have a wire, say with current coming out of the page at me, then we know the magnetic field due to it forms a circle around it, and per right-hand rule A, that's an H, right-hand rule A, the field will point counterclockwise. R is the distance from the wire to where you're measuring the magnetic field. So where is that circle? So it really is in many ways a radius in this case. Let's do a couple of examples. So here we have a wire carrying 6 amp current. 0.03 meters away, I want to know how big is the magnetic field. Now, per right-hand rule A, the magnetic field above will be pointing out at you, and below it would be pointing in. So it would be doing one of those. And I can calculate the strength of that magnetic field, mu naught I divided by 2 pi r. So that's 4 pi times 10 to the minus 7 Tesla meter per amp times the current, which in this case is 6 amps, divided by 2 pi times 0.03 meters. And that works out to be 4 times 10 to the minus 5 Tesla. Here we have a wire creating a current, or carrying current, and creating a field of 5 Tesla, a distance of 0.01 meters away. And we want to know how big is the current. So here is my field, here is my wire. I know that on this circle, the magnetic field equals 5 Tesla. And I know that this circle is 0.01 meters away. So B is mu naught I divided by 2 pi r. I'm going to rearrange this and solve for I. I will equal 2 pi r B divided by mu naught. So that's 2 pi times 0.01 meters times 5 Tesla divided by 4 pi times 10 to the minus 7 Tesla meters per amp. And that works out to be 2.5 times 10 to the 5th amps, which is a rather large current. For this next part, I want to look at 2 wires next to each other. And the best way to do this is to show you, again, a YouTube video out of MIT. In this video, we have a battery again, a knife switch, and 2 wires that are parallel to each other. Okay, notice here that if the circuit is in parallel, it means they pull the switch backward. That means that the current in both wires will run in the same direction. I guess I skipped it, but if the switch is moved the other direction, the currents will be in series, which means it goes up one wire and down the other. As you can see that the wires are repelled or attracted to each other dependent on the location of the switch. Here the current is in series and they repelled. When they're in parallel, they attract. Repel in series, parallel attract. Okay. So summarizing that, if I have two wires with the current going in the same direction, this is the parallel configuration. They attracted each other, and this would be the series configuration, in which case they repel. In the last part of this unit, I go through using the right-hand rules to figure out whether they will attract or repel. Let's do a calculation of the force on these wires. So here in this example, we are told we have two wires attracted to each other. That word attracted tells me that the currents are parallel to each other. If it had said that the two wires repelled each other, I would have known that the currents were in series. So here are my two wires with their parallel currents. I'm told they're separated by 0.2 meters. And that the current in one is 3 amps while the current in the other was 2 amps. For the sake of the example, I'm going to name my two wires A and B. In this calculation, it is a two-step calculation. So step one is to find the field due to one of the wires, I'm going to let it be wire A in this case, at the second wire. So the field due to wire A at the location of B. So field due to A is going to be mu naught times the current in wire A divided by 2 pi r, where r is going to be the distance I am away from wire B, or 0.2 meters. That's 4 pi times 10 to the minus 7 Tesla meters per amp times 3 amps divided by 2 pi times 0.2 meters. And this works out to be 3 times 10 to the minus 6 Tesla. Step 2 is to find the force, or as in this case, the force per length on whatever your second wire above was. So for me, it's B. So the force per length on wire B will be the current in wire B multiplied by the field it is experiencing. It is experiencing the field due to wire A, and the angle will be 90 degrees again. Plugging in, field or current in wire B is 2 amps. The field is 3 times 10 to the minus 6 Tesla. Sine of 90 is 1. Therefore, my force per length is 6 times 10 to the negative 6 newtons per meter. For this example, I made the choice to find the field due to A and then the force on B. Let's see what happens if I choose to do this in the opposite order. Redrawing my picture. I have my 3 amp wire, I have my 2 amp wire, this was wire A, this was wire B, and we were told this was 0.2 meters. So now I find, for step 1, the field due to B at A. So the field due to wire B is going to be mu naught times the current in wire B divided by 2 pi r, which is 4 pi times 10 to the minus 7 Tesla meter per amp times 2 amps divided by 2 times 0.2 meters. And that works out to be 2 times 10 to the minus 6 Tesla. So that was step 1. Step 2 is to find the force per length on wire A. So the force on wire A will be, force per length on wire A will be the current in A multiplied by the field that it is living in, which is the field caused by wire B, times sine theta. Theta will again be 90 degrees, so we don't need to worry about that. 3 amps times 2 times 10 to the minus 6 Tesla, which works out to be 6 times 10 to the minus 6 newtons per meter. This concludes this part. In the final part of this unit, we go over examples with the right-hand rules.